So dear colleagues, it is a privilege and an honor to introduce our plenary speaker, Professor Nathalie Sinclair, a professor in mathematics education at Fraser University in Canada. For the past 20 years, Nathalie has looked into the consequences of embodied cognition in mathematics thinking and learning, and the role of the aesthetic in the development of mathematics as a discipline, and in the understandings of both researchers and school students. She has carried out research on the ways in which digital technologies, including dynamic geometry software, and more recently, touch-screen mobile technologies, change the way people think, move, and feel mathematically. In addition to her teaching and research, she is the editor of the Digital Experiences in Mathematics Education journal, as well as Associate Dean of Research in her faculty at Fraser University. Nathalie is proud of the generative collaborations that she has been able to have with different colleagues in very different areas of research, such as Liz De Freitas, Nicholas, Joe Keefe, Alf Coles, and David Pym, with whom she has been able to research very different topics. With Liz, their book Mathematics and the Body was a really significant achievement that has led them in many interesting directions, both within mathematics education, but much more broadly. And with Nick, the digital tools they've created have been an endless source of fun, working with kids and teachers, and insight, as she will be talking about in her plenary. Nathalie is well known for her continuous contributions to the area of embodied cognition and technology in mathematics education. In particular, her work on teaching mathematics using open and interactive environments with young pupils has laid the foundation for answering questions such as, what is the value of digital technologies in supporting the teaching and learning of fundamental school mathematical concepts such as addition and multiplication? And how can we effectively use such technologies for supporting early year pupils' mathematical learning? Such questions have fueled a long debate on the value of different representations and models of school mathematical concepts offered by novel digital resources, such as touchscreen applications and symbolically structured environments. What not many people would know about Nathalie is that her first introduction to, and indeed first thought of, a career in education was through a job advertisement for a position as one of the first teachers of a one-room school newly opening on a remote Pacific island. Her job interview for the post consisted only and entirely of explaining to the school's founders what the Pythagorean theorem really means. Today, Nathalie is going to talk to us about the specifics of her recent research with touchscreen technology, but will also address how research in the specific area of technology can connect to broader themes in our research community. With no further ado, I would like to introduce to you Professor Nathalie Sinclair and her plenary talk on the technology return in mathematics education. Thank you, and over to you, Nathalie.
Great. Thank you very much, Irene, for the introduction. Hi, everybody. It's really nice to see you, especially in the chat. I wanted to begin by thanking Irene and Jeremy for their amazing, tireless, and always enthusiastic work in putting this virtual CERME together. They've done an amazing job. And I'd like to thank the organizing committee of CERME for inviting me to give this plenary address. I'm speaking to you here from Vancouver in Canada, where it's early in the morning and raining. Vancouver is on the unceded and occupied territories of the Squamish, Tsleil-Waututh, Musqueam First Nations people. So let me begin by sharing my screen. So the organizing committee asked me to say something about the pandemic, which of course is difficult to ignore given the circumstances of this conference. But before that, I wanted to speak to the title of my talk and the main argument I want to offer. Of course, the title plays on the multiple turns that we've been having in math education research over the past decades, including the language turn, sociopolitical turn, the ethics turn. Like language, politics, and ethics, technology has always been a part of mathematics and mathematics education, hence the use of the word return. Nonetheless, technology has typically been a niche part of that research. For example, in 1996, only 6% of ESM articles focused on technologies. Things did not get much better in 2006 and then returned more or less to the same level in 2016 and 2020. I think there's a problem with this. Of course, it's part of a general problem of silos of research, which I can't address in this talk. But it is also a problem that stems from people's assumption that technology is about gadgets that are new and that make things better. In this talk, I'd like to offer a different image of technology and thereby suggest some connections that could be made across thematic working groups, not only the ones focused on content areas, but also those of affect, diversity, history, theory, and teacher practice. Obviously, the pandemic does relate strongly to the topic of technology. Indeed, I cannot resist saying on behalf of my colleagues in thematic working groups 15 and 16 that we were right all along, that when we claimed that technology would save us one day. I'm kidding, of course, but we didn't predict that it would be the technology of video conferencing that would do it. More on this later. Let me begin with a little exercise that the German philosopher Matthias Horks proposes called Regnosis, or backwards forecasting. As you know, prognosis is about anticipating the future, thinking ahead. In contrast, regnosis involves looking back to today from the future. For example, in his article written in April 2020, Horks teleported to September 2020 and looked back from there, asking, what will we be surprised by? He came up with many responses, one of them being that we would be surprised that in April, we thought the pandemic would end soon and that things would get back to normal. In preparing for this plenary, I tried the Regnosis exercise in the more specific context of technology in math education, and would like to share some of the surprises I came up with. In the future, looking back, we will be surprised by how little we used our hands. For a group of people that's done so much research on how important gestures are, this is what we all look like, talking heads in our Zoom screens. I'm talking, but look at what I'm actually doing with my hand. We need to get beyond the landscape mode, perhaps. We will also be surprised by how little we moved. For people who are doing a lot of research on mobile technologies, how is it that we are all tethered to our desks, students and teachers and professors alike? Actually, things have not changed that much since the 1940s polio epidemic, when kids were tethered to their chairs, listening to the radio lessons of their teachers. And in the future, looking back, we will be surprised by how little things will have changed. The pandemic drastically increased our use of digital technologies, but as I said, it wasn't the kind of technology use that many of us had hoped for. Indeed, we have studies showing that very little mathematics exploration technology was used, which is a main area of research for those of us in TWG 15 and 16. Maybe we've been studying the wrong thing. We will certainly have much to research in the future in relation to the pandemic, given the major disruption to students and teachers, and particularly those from disadvantaged populations. That said, there are a few bright lights in the global uptake of video conferencing platforms such as Zoom. First, it's great to be able to so easily share screens and work collaboratively on digital whiteboards without waiting for students to move or find their pencils or complain about the groups that they're in. Second, it was so great to be able to call on any one of our 20 or 200 students by name, thanks to the virtual name tags below each one of them on the video feeds. Third, it's great to have a third channel of communication that can run parallel to teacher talk, by which I mean the chat function. In the past, this could sometimes be accomplished by passing notes, but that was time-consuming and especially dangerous. The parallel use of chat multiplied the forms of communication in online learning. For example, in this screenshot of a lesson on square roots, the whiteboard is being used as a shared annotation space with each color belonging to a different student. As the teacher talks, there's a whole conversation going on in the chat. One student wants to know how to use annotation, another wants to suggest a solution, another wonders why the teacher has written 98 on the whiteboard. This back-channel communication shifts the distribution of agency between students and teachers. It enables students who might be uncomfortable speaking up to participate through writing. It allows for local expertise to develop, and it provides multiple representations of information. A year ago, the functionalities of platforms such as Zoom might have been interested participants of TWG 15 and 16, which together would have attracted about 7% of CERME conference goers. This year, almost everyone is interested, or at least they feel like they should be interested. For this reason, I will take this opportunity to mainly address the 93% of participants who would not have chosen TWG 15 and 16. For at least 2 centuries, technology has occupied an awkward position in culture. There have always been those who championed it and argued that new technologies will make things better. At the same time, there have always been the skeptics, those who fear it, doubt it, find it threatening, argue that new technologies will make things worse. Historically, the former group has been allied with the sciences and the latter with the humanities. Scientists think in terms of progress, usefulness, the possibility of mastering tedious or difficult parts of our lives. The humanists think in terms of preserving culture, protecting human agent autonomy, and how we will become servants to technology's demonic ways. This happens in math education too. On the one hand, new technology is touted for making learning and teaching easier, better, faster. On the other, it is critiqued for making things worse, causing the loss of basic skills, making things less equitable, turning us into automatons. Like any dualism, this one can be disrupted, exposing the iceberg below. Indeed, a third perspective acknowledges both the utility and the loss that new technology brings about, but rather than position it as master or slave, understands it, following Simondon, as a theme in human experience, like art, homo technicus. In this way, technology is not simply a gadget, but interwoven into our history, our material culture, and our micro and macro evolutions. I therefore propose that instead of talking about technology making things better or worse, instead of ascribing the bettering or the worse to the new, that we focus on technology as simply making things, what these 2 statements have in common. In this light, technology becomes a way of rereading history, of understanding the changing nature of mathematics, as well as the changing nature of mathematics teaching and learning. For example, think about how dynamic geometry environments have helped us remember and appreciate the dynamic performative nature of ancient Greek mathematics, drawing in the sand. Think about how video conference technology reveals our normal, well-encrusted participation structures in the classroom. Think about how 3D pens help us notice how mathematics has been for millennia a 2D inscription practice. It is from this perspective that I would like to talk today about my recent research with two multi-touch applications called touch counts and touch times, in which users engage in a kind of gestural arithmetic. I have had the pleasure to collaborate with many colleagues on various aspects of these applications, as you can see here. I will be touching on some of these studies later in the talk, but my main aim is to focus on what these multi-touch applications illuminate about the nature of knowing, the nature of being, and the nature of valuing. Specifically, I will be undertaking the three following investigations: a technology-inflected history of knowing number, or why fingers matter, a dissolving of the learner conceptual boundary, or how gestures matter, and an inquiry into the intimacy of touch, or why feelings matter. These are epistemological, ontological, and axiological questions about technology. These applications were both developed with the software designer Nicholas Jockiffe and arose directly from the touchscreen functionality that was newly available in 2010. This picture shows you more or less the setup I'm going to use now to show you touch counts. And it's a shout out to the incredible creative teachers around the world who have figured out creative ways of being able to show technology. This is a picture that was sent to me by Annette Rouleau, and I thank her for inspiring my own presentation. So I'm going to quickly switch out of my PowerPoint and move to an external camera. All right then, so this is touch counts, and touch counts has two worlds. One is mainly for ordinal numbers and one is for cardinal numbers. In the ordinal world, the main idea is that every time you touch the screen,
2, 3, 4, 5.
You see an object, you see the numeral, you hear the name of the numeral, and you touch the screen.
6, 7, 8, 9, 10.
And of course, since it's on the iPad, we don't have to stay with the 10 fingers of our hands, but can
11,
continue
12,
going.
13, 14, 15, 16.
So the one-to-one correspondence of Piaget here between pointing finger and object becomes a one-to-one-to-one-to-one correspondence between pointing finger, number name, number symbol, and individual object. The idea here of the gravity, having the numbers go away, is so that we can ask questions like, how can we put 5 on the shelf?
1, 2, 3, 4, 5.
Most kids can count to 5 even at 3 years old, but that doesn't mean they know that 5 comes before 4. No, it doesn't. It comes after 4.
1, 2, 3, 4, 5.
So with Einat Haimetsuyanam, we've been studying how this process of putting a number on a shelf can help children develop a reification or objectify number. You can put 5 on the shelf, but it's also quite easy to put 10 on the shelf.
6, 7, 8, 9, 10.
Or 15.
11, 12, 13, 14, 15.
With Alf Coles and I, we've studied how asking kids to put 15 or 25 or 85 on the shelf becomes a way to explore place value with them from an ordinal point of view, starting in grade 1. I've been touching one finger at a time, but of course we can also multi-touch.
19, 20.
And that means I can multi-touch with my own fingers, but I can also get the help of somebody else.
22, 24.
Thanks, Nick.
25.
Multitouch becomes very important in this world, where the act of putting several fingers on the screen at the same time gives you a cardinal quantity. We call these herds. Again, you see the oral feedback as well as the symbolic feedback and the touch feedback and the visual feedback. The all-at-once task that Uli Kortenkamp and Silke Ladel devised requires putting all 4 fingers at the same time after you count out, maybe to 5, and then put them down. As David Pym and I have shown, when children successfully produce 4 or 5 or 7, they are engaged in a gestural subitizing. With cardinal quantities created, the pinching gesture can be used to add these herds together.
9.
After the sum has been made, the color shows a history of where this 9 came from.
12. 19.
Francesca Ferrara and Katie Savioli have shown how working in pairs or even groups of 8, where each hand contributes a number, provides a rich context for composing and decomposing number.
3.
And here we can do some proto multiplication of 5 times 3. Once we have a herd, the inverse gesture of pinching, becomes the gesture for taking away or subtraction.
11.
Similarly,
15.
the inverse gesture of multiplication, multiplying, leads to
5.
equipartitioning. Therefore, each arithmetic operation can be expressed from a specific gesture and function metaphorically like the operation itself, effectively replacing the static symbols of plus, minus, times, and divide with temporally enacted but precise movements of the hand. By offering both ordinal and cardinal ways of manipulating number, children can solve the same task in both worlds, which, as Anna Bacalini-Frank and Gemma Carotenuta and I have shown, allows them to work at each and every one of the number sense abilities identified in the research literature in a holistic way. I'm now going to move on to touch times, which was meant to extend the gestural arithmetic developed in touch counts to multiplication. Of course, multiplication, as you know, has been identified by researchers as a crucial concept in students' mathematical progression. With the well-documented weakness of the repeated addition model of multiplication, we designed 2 worlds that offer different models that could be accessible to young children, with the idea that they would explore these models at the same time as repeated addition and not afterwards. In both worlds, 2 hands are needed in order to produce a multiplicative relationship, with each hand expressing one of the 2 covariant relations. In the graphifying world, which is adapted by the Davidov unit of unit approaches, we first use one hand to make a unit and then the other hand to copy that unit or multiply it. Here we have pips and here we have pods. As you can see, each one of these pods is a clone of the pips. Moreover, while I can add more pods, which influences a more additive way of thinking, I can also change the number of pips. And we can see that each new pip spreads across each and every one of the pods. While most North American primary teachers introduce multiplication as groups of, Graphify at first seems backwards to them, and sometimes even downright wrong. However, in research with Sean Chorney, Sandy Bakos, and Janan Gunesh, we have found that it is precisely this backwardsness of the design that allows them to rethink their own understanding of multiplication and begin to value the opportunity to develop flexibility amongst their students. In the Zaplify world, we use the Cartesian model of multiplication. Here, the screen is divided into two triangles with hand touches along the bottom and the side. Hand touches along the bottom create vertical lightning rods, and hand touches along the side create horizontal ones. The intersection of the lightning rods produces our product. Again, the co-varying of the two quantities is highlighted, as is the fact that the product, the intersections, are different kinds of quantities than the lines. I want to point out that one of the major impediments in communication among researchers around technology has been the limit of the static printed form in which our journal articles are written. This has allowed the temporal, rhythmic, and motoric aspects of making things with technology be trumped by static images. So as we can see in this, if you saw this screenshot of Zaplify in an article, for example, you would probably think, oh, that's just the array model. You would be focusing on the product rather than the performance, which happens in time with hand-eye coordination, muscular engagement, touch, and affect. The reduction of the static image is a problem for many technologies, not just touch counts and touch times, but that our willingness to overlook the performance is tied up not just with the hegemony of print, but also long-held assumptions that what matters in mathematics is that which is still and pure, untarnished by sweaty fingers and messy movements. This leads me to my first investigation. For decades and decades, still sometimes today, educators have tried to dissuade children from using their fingers in the mathematics classroom. The thinking goes like this: if the goal is to get Piagetian abstract concepts, then fingers not only constrain learners to the sensory motor stage. Even sociocultural theorists are in a hurry to replace fingers with words and symbols. However, when we look at anyone learning, talking, thinking about mathematics outside of the regimented classroom, we see fingers being used. Whether at the marketplace, kitchen table, when doing theoretical physics, and even occasionally in classrooms, people doing arithmetic need their fingers right out in front of them. Research has shown that when people are not allowed to use their fingers, they make more mistakes when counting. We think with our fingers. Different cultures have developed powerful ways of doing arithmetic with their hands. Here's a typical North American way of counting, starting with the thumb, going to the pinky, each time adding one more. Here's a slightly different way of doing it from East Africa, where we can see the nice connection between 2 and 4. This is a much extended arithmetic beyond 10 that we see in Indian schools. You can get to 30 with your 2 hands. In this old Chinese system, every knuckle counts. You can get to 90,000. It's the little bump on your thumb. And in Papua New Guinea, the biggest number is 27, but you get to use your whole body to get there. We have thought with our fingers for millennia. As it turns out, there's good reason for this. Recent imaging done by neuroscientists show that there is an overlap in brain activation between finger discrimination and arithmetic processing. While calculating, the finger-related area of your brains are activated. The biological evidence is pretty clear. Counting, the production of numbers, isn't just a mental activity, it's a physical one. In touch counts, we are recuperating the fingers, which have been shoved away by centuries of Cartesian mind-body dualism. And we are extending the fingers so that we're not limited to 10. With their fingers, children make numbers by touching the screen, while children can also touch counters and cubes and teddy bears used in primary schools. These objects don't respond in words and symbols like touching does in touch counts. Our research has helped us recover the technology of the finger. and its role in arithmetic thinking. It has highlighted the fact that mathematics and technology are inextricably linked, as Brian Rotman has argued, and that if this is sometimes forgotten, it is only because the technologies of common practice have become invisible, like pencils, blackboards, textbooks. We will forget these technologies in the same way we've forgotten logarithm tables, slide rules, overhead projectors. From this point of view, the mathematical landscape is a graveyard of past technologies used to grapple with and to make things mathematical. This technology-inflected history of mathematics has significant repercussions on our learning theories. For example, consider Brunner's theory that goes from the inactive to the iconic and then the symbolic representations. Each is associated with a particular technology of his time: physical objects, images, signs, each one independent from the other. But in touch counts and touch times, we see a simultaneous expression of action, image, and symbol that should make us wonder what sequence in which students can and could learn. Using touch counts, 4-year-olds are making, reading, and using symbols right from the start. They're putting 100 on the shelf. They know that getting to 200 isn't just one more touch, but it's going to take a long time. Similarly, technologies such as touch counts and touch times disrupt the Piagetian move from concrete to abstract, from the sensory motor to the formal operational, because they enable and encourage doing and thinking that is concrete and abstract, that never gets over the sensory motor. And this perhaps is why children can learn place value in grade 1, seemingly skipping over the symbolic or concrete operational before cardinality or addition. My proposition is thus that the development of number sense in every context depends on a particular technological infrastructure. Readings that ignore this infrastructure, from general learning theories to more particular teaching and learning trajectories to their application and curriculum design, are insufficient to the evidence. If this wasn't obvious before, it was perhaps due to the hegemonic nature of paper and pencil, which has endured so long. But with the rapid change of technology being used, especially outside of the classroom, we will have little choice but to recognize the multiple paths that teaching and learning can take in relation to particular technological infrastructures. Can we really separate the learner from the tool, or the tool from the mathematics? This leads me to my next investigation. One of the things that both touch counts and touch time highlights is the extent to which mathematics has been a one-input discipline for millennia. From the stick drawings in the stand, to the pencils on paper, to the calculators and the keyboards and the mouse. It makes me wonder, what would mathematics have looked like if it had been a 2-input practice earlier on? Might functions have arrived beforehand? Would we have studied spirals instead of ellipses? These images also remind me of Merleau-Ponty's story about the blind person and the cane, which he uses to ask, where does the blind person's self begin? At the tip of the cane? At the handle of the cane? Or at some point halfway up the cane? These questions are nonsense. We cannot draw a determinate line across this dyad, since any cut will sever the part of the systemic circuit that determines the blind person's locomotion. Merleau-Ponty asks us to think blind person cane instead of blind person with cane. Similarly, we should be thinking student tool. This triangle is a very common spatial imaginary for the relations between learners, tools, and concepts that we see often in mathematics education. But with Merleau-Ponty, we might imagine something like this. Mathematics education research has evolved enormously in its thinking about the body, thanks to recent theories in embodied cognition. And in parallel, we have advanced in thinking about our tools, as is evident in the work of my colleagues in TWDs 15 and 16. However, thinking learner tool is another matter. An early learner tool thinker was Froebel, whose gifts are a staple amongst mathematics educators. but whose study of the hand gift is much less widely known. Here's a picture of the third gift, which many of you have seen. And here's what Froebel thought the hands would be doing in interaction with that gift. In other words, he wasn't just interested in the tool, the physical objects, the blocks, or even in moving the blocks, but in the ways that the hand would be moving as a consequence, in concert. As Brent Davis, Oilam Ing, and I have written, it is more about structured ways of moving the body than simply moving structures. Where the blocks differ from touch counts and touch times is that in the latter, the movements of fingers and hands are designed to express mathematical relations. The hands and fingers are used in a very specific way, constrained mathematical way, which Eva Jablonka and I have called operational templates. And from this perspective, the traditional distinction between body, tool, and mathematics begins to blur. Going back to our spatial imaginary, we might be thinking like this. Along these lines, another aspect of gestures that touch counts and touch times has complicated is the strict separation of hands as sign makers that can be found in linguistic informed accounts of gestures, which dominate math education research, and hands as manipulators, that is used in the field of human-computer interaction, but also by treatises on painting and sculpture. With Jürgen Streeck, I'm interested in disrupting this binary and studying how gestures are a continuous phenomenon that go back and forth between manipulating and messaging. The hand is part of our bodies and it's a tool. To highlight this, we've been accumulating many examples in a wide range of contexts in which children's structured ways of moving their bodies with touch counts and touch times have become communicative devices that help them explain their multimodal understanding. As we can see here, where the boy making the pinching gesture that he knows from touch counts. Here, the touch times gesture is used to make and verify, but also to retouch and relive the experience of multiplying. Indeed, this has been particularly interesting with touch times, whose design relies on the use of two hands for expressing multiplicative relations. The two hands are physical embodiments of the two quantities that co-vary in multiplication. Just as learning how to tap one's finger on the screen as a 3-year-old is a physical precursor to differentiating one's fingers and learning number, learning to use both hands, one for horizontal lightning bolts and one for vertical ones, is a physical instantiation of holding and expressing two factors. How we interact with the tool shapes not only the tool, but also our hands and our minds. This claim is obvious to anyone when they think of evolutionary timescales. Our rotating shoulder socket co-evolved with trees we use to swing in, and in turn become tools we can use to throw overhand projectiles at prehistoric rabbits on the savannah, which in turn encourages our inductive thinking into conjecturing where the rabbit will be when the spear arrives, rather than where the rabbit is now that the spear is departing, etc. But evolutionary trajectories are just the vast accumulation of momentary experiences. So if we acknowledge this mechanism in the span of millennia, we must acknowledge it equally at play in the span of instances, and in our context, in the span of mathematical classrooms. My proposition is that redrawing and occasionally even erasing the borders, separating our traditional constructs of learner, concept, and tool, offers productive new insights into where and how mathematics learning occurs. Rather than map our learning concepts, tools, learners' concepts, tools as autonomous nation states that negotiate only through carefully drawn treatises outlining the rules of transfer or representation or interiorization or mediation, we could start looking at how alliances, combinations, and even site-specific unifications of these somewhat artificially separated constructs generate productive new insights. If I can offer a paradigmatic example of what I suggest drawn from outside of mathematics education, consider how our theories situate the vast majority of us who rely on eyeglasses or contact lenses to correct our vision. Under a traditional reading of this isolation and separation, these constructs, we ourselves appear as functionally incapable learners, actors stumbling in the dark, entirely separate. Spectacles then appear to as some sort of miracle promising technology that feature some sort of representation of the external world. Our traditional theories will then spend a lot of time complicating this representation and worrying endlessly about how on one hand about its fidelity to the abstraction it claims to represent, and on the other, the vast variety of misinterpretations and obstacles that hypothetical users might encourage if they try to put them on. These theories are, on occasion, factually predictive, but none of them allow us to productively see, or if I can squeeze the eyeglass example to its limit, to focus on how the combination of the person and eyeglasses is largely unproblematic and functional actor capable of astonishing new perceptions and through them astonishing new agencies. And this in turn leads me to my third and final investigation. When we were first working with 3 to 5-year-old children and asking them to make 4 all at once, they invariably used 1 finger at a time, sequentially touching 4 times. Placing 4 fingers on the screen all at once was something they learned to do over time. Eventually, after repeatedly having been touched 4 times simultaneously by the screen, the children could successfully make 4 all at once, could make 4 in the air, could name a group of 4 objects, and eventually join 4 with other numbers. The making of 4 all at once was a tactile experience, the touch version of subitizing. This is an example of touch being used as a mathematical sense. There is something special about this sense. It not only requires actual contact, unlike sight or sound, but because of this, it is a double sense. As you touch something, you are touched by it. Significantly, though, while you can touch a textbook, it doesn't touch back in the same way as touch counts, because the textbook does not produce anything as a result of your touch. It doesn't communicate mathematically with you through touch. This raises the question of what can be sensed in mathematics, and in turn, what we think makes sense in mathematics. What is common sense? This association of mathematics with the senses has had a troubled history. Recall Descartes' disembodied mind, which had little uses for the senses. Just a century ago, the mathematicians of the Bourbaki banished images from their textbooks. Like the sense of sight, the sense of motion was suspect. For Plato, moving images were almost blasphemous. Descartes was willing to consider the motion of 1 object, like the compass, but not 2. Bertrand Russell insisted that points and triangles stay put. Now, both the senses of sight and motion are fully endorsed by the mathematics education community. And in the past decade or so, sound has also emerged as a sense for mathematics. As Lulu Healy has shown with her sound calculator, which is the oral counterpart to the color calculator, and with which you can hear fractions. Here is 1/7. Images, motion, and sound are technological evolutions. As they have gained in prominence, we have realized that they were significant to historic mathematical practices, like the kinetic work, of Archimedes, the visual proofs practiced by Chinese mathematicians, the highly dynamic concepts of mathematical objects amongst indigenous people like the Mi'kmaq. As Elizabeth de Freitas and I have argued, technology-inflected history exposes minor mathematical practices that have been cast away, ignored, or seen as illegitimate. Further, the more we learn about what can be sensed in mathematics, the more we understand about what is taken to make sense and for whom. The aesthetic is political, and technology is right in the thick of it. Touch counts and touch times both bring to the fore the sense of touch and its potential as a mathematical representation. But in its intimate way, touch cannot just be thought of as yet another sense. Indeed, it is in its affective nature that seems to me most interesting. In touch counts, we have observed over and over again, with kids as well as adults, the compulsion to touch repeatedly and rhythmically, to get to 100, 1,000 and beyond, the compulsion to pinch herds as if the screen were pulling on the fingers, wanting to be touched. In touch times, touching the screen in Zaplify literally produces a jolt of electricity, a feeling amongst some of students of power and magic. If our theories in mathematics education, especially in the area of technology, have focused almost exclusively on cognition, it is perhaps because we have overlooked the panoply of senses at play in students and teachers' use of technology, and ways these senses, and perhaps especially touch, produce new distributions of affect relevant to teaching and learning. My proposition is that at any moment in time, technology powerfully reflects and diffracts the mathematical values that dictate what it means to make sense. The political implications here cannot be overstated if we follow feminist, queer, post-colonial, and critical race theorists who have shown how Western images of reason, and hence of mathematics, have been based on a logic of exclusion. I'm not saying that using touch counts and touch times will lead to less colonial or less oppressive mathematical experiences, but simply that these technologies play into and help illuminate long-standing assumptions about what is valued, what has been valued, and what could be valued as mathematical practice. In closing, I have focused on rethinking the ontological separation we have imposed on learners, tools, and mathematics. This is just a particular example of a much broader scholarly phenomenon in which scientists, social scientists, and humanists alike are beginning to appreciate the fact that treating nature and culture separately is no longer tenable. For us, that means, for example, that separating the physical individual from the sociocultural is no longer tenable. You may think, yes, of course, that's true, that's obvious. But in almost every article I read in mathematics education, one point of view has been chosen over the other. And rare are the articles that give the material its full ontological status. Of course, specific constructivists and specific sociocultural theories provide important insights, but they will only matter if they are open to heterogeneous fields of dialogue. In that light, I have a suggestion to make in relation to technology. Given the opportunities and dangers of new technologies that have been documented, more alliances need to be made between those of us working in technologies and those of us working from more critically oriented perspectives. To those of you informed by post-structural and critical theorists, remember that technology is inextricably linked to issues of power, colonialism, and marginalization, that it is not a passive player in that drama, that it is not just a function of discursive regimes of power. By thinking technology as more than a gadget, making things better or worse, we can expose and disrupt well-encrusted assumptions about how things are, and therefore point to how things could be. To my colleagues in TWG 15 and 16, we have remained rather tied to our constructivist theories. Indeed, very, very few of the articles published in technology-specific journals have addressed the pressing issues raised by our colleagues working with more recent sociopolitical paradigms of inquiry. If technology enables multiple learning trajectories, some presumably favoring certain learners and teachers over others, thinking through the politics of choice becomes even more imperative. Here are some examples of research that seek overlap and alignments between these two areas of research. which have remained rather niche, but for different reasons. This article recently published in 2019 in Digital Experiences Mathematics Education, and this is the introduction to a special issue in the Canadian Journal of Science, Mathematics, Technology, and Education. New research in algorithms, ethnocomputing, in technology for inclusive education, and in critical data literacy are also examples of such alignments. I hope that in offering a broader view of technology as being about making things, I've been able to make more visible the underbelly of technology, its long history with humans and its defining history for mathematics. I also hope that I have sparked some new productive alliances. And before I end, I'd like to thank these wonderful colleagues who have worked with me, from whom I've learned a great deal and I've enjoyed learning with. Thank you very much.
Thank you so much, Nathalie.